Hello everyone. So welcome back to the good stuff that we've been doing. Today in this video, we're going to try to find the value of this integral. We're trying to show that this is equals to pi over 4. And on my Facebook page, when I posted this video, one of my Facebook friends actually used the series for sin x, which is x to the 2k plus 1 divided by 2k plus 1 factorial. So my friend uses, and when you plug in log x over, so basically sine of log x divided by log x here. This is the sine of log x divided by log x. You would obtain the series to equal, it would equal the sum as k runs from 0 to infinity of negative 1 to the k. So you have logarithm of 2 to the k x divided by 2k plus 1 factorial. So if you plug it here, and switch summation and integration, you are going to get something interesting. So that is its own solution to this problem. So probably if you check my Facebook page, you are going to find the right solution. But for now, let's enjoy this integral here. I'm going to use a method I usually use, and that is double integration technique. And the way that would flow is that I'm going to use the fact that negative 1 over log x is equals to the integral from 0 to infinity of x to the y dy. So if you go back to calculus 1, you can actually evaluate this integral, because if you observe the integral from 0 to infinity of x to the y dy, notice that x here is a constant here. So basically we write this as the integral of 0 to infinity of e to the logarithm of x to the y, right? Yes. So e to the logarithm of x to the y, then dy. So you could write this as the integral from a 0 to infinity of e to the log x times y dy. Now, this is basically trying to do the integral from 0 to infinity of e to the ax dx, whereby this is 1 over e to the ax. So this will be, we're going to evaluate 1 over log x, then you would have e to the logarithm of x to the y, e to the logarithm of x to the y. So you're going to evaluate this as y runs from 0 to infinity, which means you would have to evaluate x to the y divided by log x as y runs from 0 to infinity. Now, notice here that x lies between 0 and 1. That is the most important concept here. So if x lies between 0 and 1, when x to the y goes to infinity, you will have a 0. So the first one would be a 0 minus 1. Now, when y is 0, you have a 1 over log x. So basically, this has proven what I claimed here, that negative 1 over log x is actually equal to the integral from 0 to infinity of x to the y dy. So that is that for you. Now, let's see how we could use this fact to actually solve this problem, because this is basically just one way to represent this denominator. But let's see how we could use it to solve this problem in the general sense. So let me write down the integral. So let me take it from my paper here. So just hang on there. Okay, so I'll start afresh here so that the old work does not disturb me. So here, observe that the integral from 0 to 1 of x, 1 plus x divided by log x, then you have sine of log x, sine of a log x dx. This is equals to the integral from 0 to 1 of x plus x squared times what? Then you would have sine of log x, but then you would have times negative integral from 0 to infinity of x to the y dy, then you have dx. So this integral has been transformed to this. This is easy, then this is a bit complex, but then we like complexity, because from complexity, then we are going to find the general pattern, and then everything will crumble to pieces. So proceeding as before, this would be basically, you can bring out the negative, and then you have integral from 0 to 1, then you have integral from 0 to infinity, then you have here you have x to the y plus 1 log x. Yeah, so you have x to the, so you have a x to the y plus 1 log x. Okay, no, just x to the y plus 1, then you have plus x to the y plus 2, then you have sine of log x, then you have the y dx. Now we could make some substitution. We could take u to be log x. Yeah, we could make that substitution obviously. So take u to be log x. Now, if that is the case, then what happens to our x? X would be e to the u, then dx. Then basically when x becomes 0, e to the u will be negative infinity, right? So you have a negative infinity. So, and when x become infinite, let's see. Okay, wait. We are actually okay. Let's switch integration and differentiation. So you are going to have this as negative times the integral from 0 to infinity. Then you would have the integral from 0 to 1 of x to the y plus 1 plus x to the y plus 2. Then you would have sine of log x, Then you would have dx, obviously dx. Then you would have dy. So we are going to take evaluate dx first before doing dy. Now here, observe closely here that if we take x to be, if you take u to be log x, then the limit of integration is from 0 to 1. For when x is 0, when x here is 0, u will be negative infinity, and when x is 1, u have to be 0. So basically, you would end up with a negative integral from 0 to infinity of what? Now you have integral from negative infinity to 0. Then you would have e to the y plus 1 sine, you have e to the y plus 1 sine u. But let me see. Which x is e to the u. So x to the y plus 1 would be e to the y plus 1, obviously. But you have to observe something here, that when you take dx, it will be e to the u du. So from e to the y plus 1, we will have an extra e to the u. So it will definitely be e to the y plus, so here you would have e to the y plus 2 times sine x times e to the y plus 2u, e to the y plus 2 times u, then you have sine u du, then you have plus the integral. So you have plus the integral from negative infinity to 0 of e to the y plus 3. Then you have u sine u, then du, then everything by here is dy. Now also observe that we have if you remember from calculus 1, that the integral from 0 to infinity of e to the ax sine x is going to equal, I think a square over a square plus 1, then you have a sine x minus cosine of x, something like that. So there's an antiderivative for that. We're going to use that formula here. Okay, so you have negative times integral from 0 to infinity. So in this first part of this problem here, you would have something like this, e to the u plus 1. So you have e to the u, y plus 2 times u. Then you would have divided by y plus 2 square plus 1. Then you would have what? You have sine, you have this y plus 2 times sine u. So you have y plus 2 times sine of u, then minus cosine of u on this first part here. And you're going to evaluate everything here from negative infinity to 0. And then we're going to add this up with the integral, we're going to add this up with e to the y plus 3 u, all divided by what? Y plus 3, and take the square, then you have a plus 1, and then you have a y plus 3 sine u minus cosine of u. So if you evaluate the limit from, again, negative infinity to 0, everything is dy. When all is said and done, you should end up with something like this. Should end up with this is equals to negative times integral from 0 to infinity of what? On the first part, you have a negative 1 over y plus 3 square. Then you have 1 over y plus 2 squared, then 1 over y plus 3 squared plus 1. So everything is dy. So now we have a very simple integral. Now we can solve this. Of course, the whole expression cancel out. You have your Okay, so the first integral will be 1 over y plus 2 squared plus 1 dy, then plus the integral from 0 to infinity of 1 over. So you have a y plus 3 squared plus 1 dy. So this is not too hard to work out. The first one, you would have, if you evaluate this integral, this is very elementary, you have the tan inverse of y plus 2, and this is from 0 to infinity. And this is a tan inverse of y plus 3, and this is from 0 to infinity. So you would have a pi over 2 minus tan inverse of 2. Then you have plus pi over 2 minus tan inverse of 3. So when all is said and done, you have pi minus tan inverse of 2 plus tan inverse of 3. So essentially you would have pi minus, now tan inverse of 2 and 3, this would be pi plus tan inverse of 2 plus 3 divided by 1 minus 2 times 3. So that would be negative tan inverse of -1, which is negative times negative pi over 4, which is pi over 4. So that is that. So thank you very much for watching, and please do subscribe to the channel. Bye.